Hello, my name is Stefan Kaalen, and today I'm going to talk to you about our paper, A Stochastic Extension of Stateflow. And it's a paper I wrote together with Anton Hampus, Mattias Nyberg, and Olle Mattsson. And we did this with the collaboration of KTH, Royal Institute of Technology, the Scania Vehicle Development, and with financial support from FFI. Now, first I'm going to give some background into model-based development in industry. So, systems today are becoming increasingly complex, and this is a change that has happened over time, and it's pushed even further by new technologies such as autonomous vehicles. With this increased complexity in the system, model-based development has grown into a major part of research and development in industry. Now, one tool that is very well spread in the industry for modeling and analyzing systems is Simulink Stateflow within MATLAB. When performing model-based development, probabilistic properties are quite important in many areas. For example, one area that we focus a lot on is safety critical systems, where probabilistic properties are of great importance to be able to make realistic models of real-world systems. Now, Stateflow, as I said, is very well spread in industry today, but it unfortunately does not have explicit support for probabilistic properties, which is why we, as a first contribution, present an extension of Stateflow with this support. So now let's talk about Stateflow for a moment. So starting with MATLAB, MATLAB is a language and environment for technical computing, and it has more than 5 million users worldwide. Now, Stateflow is a tool within MATLAB for modeling state machines, and it's an industrial standard practice in many areas, for example, the automotive industry. And it has explicit support for modeling temporal properties, time-depending things. However, as I mentioned, it does not have explicit support for modeling stochastic properties. Now, there are, of course, other tools available which can be used to model systems with explicit support for stochastic properties. However, these tools are not as well spread in industry as Stateflow is, which is why we have chosen to build our work upon Stateflow to make it easier for the industry to take in and be able to use the work. Now, we start by looking a bit on the Stateflow syntax to then move on to see what we have extended it with our stochastic properties. So this is a simple Stateflow model. So we have a couple of states here. You can see S1, S11, so on. And then we have a couple of transitions between the states. And these blue arrows are what's known as default transition, which says that if S1 is entered, then S10 is entered also by default. And if S2 is entered, then by default, S8 is also entered. Now, here we see an example of how a transition looks. So we have 3 parts. We have a set of condition events, we have a guard, and we have a broadcast event. So the set of condition events, it says that for us to be able to transition from S8 to S9, we must receive either the event E1 or E2 from some other place in the model. Now, the guard here says, as you can say, after 1 second, and it means that we need to be in S8 for at least 1 second until we can reach S9. So once 1 second has passed, this guard gets evaluated as true, and then we just wait for to receive one of these events for the transition to happen. Now, the final part here, the broadcast event, it's sent to the rest of the system when this transition happens and can possibly trigger another event, another transition in the system. So those are the major parts I want to present. And I also want to mention that we actually focus on a subset of Stateflow, and this subset has been chosen to by looking at a lot of case studies. and seeing what's actually the most important part to have in our models to be able to model a wide array of systems. We have also done it in the idea of making a safe subset. So our subset has no variables because we have found that in all the case studies we have made, it was quite easy to handle them without variables. And we also, in order to align with guidelines for making a safe subset of Stateflow, only allow one type of events. So basically, we can only send events in one way, while in the complete Stateflow, you can send the events in two ways. But we felt it was not really needed, and it's not recommended in the modeling guidelines. So let's move on to SSF models then. So stochastic Stateflow, SSF, is our stochastic extension of Stateflow. And it is extended with stochastics in two major ways. So firstly, we have the junction probabilities. And this is what you can see here. So all of this is actually one transition, but the transition has two possible destination states. And so you can see you put the condition events here on the arrow into the junction, and you also put the guard here if there are any, isn't it? And then you put the probability that that destination state is chosen together with the broadcast events that will be sent on the arrow outgoing from the junction. The other major thing is that we allow CDFs in after expressions. So while MATLAB in the after expressions has constant times, like we see here, here, and here, that we have a specific time when the transition will happen or when the guard will get evaluated to true, at least. We can here allow a distribution instead. So we say that this guard becomes evaluated at some time distributed with a log normal function with parameters 2 and 1 after we've entered S3. Yes. So, and we also presented an operational semantics in our paper, an operational semantics for SSF models. And I can mention that Stateflow in itself has quite a complex semantics. So a lot of work was put on building this operational semantics. And it works by describing how the configurations of the system changes when different things happens. And the configuration is basically give a set of active states and an evaluation of timers. So basically of the all after expressions, it gives an actual time instead of the probability distribution. And here we can see examples of how some of the rules can look. So this one says that if we don't broadcast an event, then we will not change the configuration. But if we broadcast an event, we may change our configuration to another because that may trigger other transitions. Now, our second contribution was that we implemented support for SSF into SMP2. And the maybe main functionality here is the transient analysis. So with that, we can compute the probability of ending up in a certain state. And we call this state down state, as you can see here in S11. And usually when we're working with safety, this corresponds to system failure. So you can find the probability that a system failure has occurred after some time. Now, finally, we in the paper present a case study based on a system from Scania. And we could actually use the tool to produce these plots to find that after a lifetime of 45,000 hours, the probability of having a system failure is below 5 to the power of -7 with a confidence bound of 95%. So I will now go into the second part of the presentation where I'll go into a little bit more detail. So here I am planning on discussing a bit more exactly how the syntax of the SSF models really look. So here we see the abstract syntax. Now I'll connect this to the graphical syntax we see here. So we actually specify our models in Stateflow and then use SMP tool to run them. So I will go through each of these components in its own time. So we start with S here, which is the set of states. So as you can see here, we have 11 states, which is clearly visible. And there's also actually in the abstract syntax 12th state, which is the root state here with S1 and S2 as its children. This state is implicit in Stateflow, but it's present in the abstract syntax. And then we have S down, which is a subset of the states that represents down states. And as we see here, we only have S11, which is our down state, and what usually represents a system failure in our case, looking at safety. Now, I should also mention, considering the states, that there's actually three internal functions within the state domain here. So we have a type function saying whether a state is an AND state, an OR state, or a basic state. So basically a state without children, which is a state without any other state within it. So for example, S6, S7, S11, S8, those are all basic states. And then we have the states that have children. And S1 is one example of this. And as you can see, its direct children here has a hard line on it. And there's also a blue arrow here to one of the states. This means that S1 is an OR state. So we're always either in S3 or in S10 or in S11. While, for example, S4 here is an AND state, which you can see by this dashed line here, and there is no initial arrow on any of its states. And that means that when S4 is entered, so is S6 and S7. And in the same manner, you can see that when we're in S1, we are also in S2. So we're actually in some state here, and we're also in some state here. And then we have the children function of the states, which simply maps a state to its direct children's. So the children's of S1 are S3, S10, and S11. And finally, we have an order function that orders two states with the same AND parent. So for example, S6 and S7 here, as you can see, are ordered, and this gives an order of priority. The same thing goes for S1 and S2. So this means that if a transition happens in S1 at the same time as in S2, we're prioritizing first doing the one in S1. Sorry about that. So next I will go through the initial, and as I mentioned, this is this blue arrow that says which is the default starting state inside an OR state. F here is the set of CDFs. So here we have a log normal CDF, we have a exponential CDF with a parameter A here. And we also have three degenerate distributions here. So these are the after expressions we saw in Stateflow, but considering everything as CDFs, we see these exact times as what we call a degenerate distribution with a Heaviside step function. So this has a Heaviside step function in 0. This one has a Heaviside step function in 1, and so on. And then we have our guards, and those are built in the same manner as in Stateflow, with the difference that we can have distributions within our after expressions. So they can be as easy as this, and they can also, just as in Stateflow, be a composition of basic guards. So this can be an AND and an OR composition, and we can also put NOT on things. And the basic elements here is either on the form in, saying that we need to be in state S9 here, or as a after expression of a CDF. And then we have our set of events, which is simply E1, E2, and E3 here. All events that are either received or broadcast, either condition event or broadcast event on any transition. And then we have, of course, our transitions. And as I mentioned previously, we have a set of condition events. We have a guard. And for each possible pair of destination state and broadcast event, we have a probability. So here we have probability 0.8 of not sending a broadcast event and reaching S5, and the probability 0.2 of sending the broadcast event E3 and reaching S10. So now I will go through a bit more about how do SMP actually perform this simulation of SSF models. So this is actually a two-step thing. So the first thing that happens is that the model is transformed to remove hierarchies. And this is the same thing as saying that no OR states can no longer have OR children. So as you can see here, we have a hierarchy here. So we have an OR state, and we have one of its children is in itself an OR state, and this is what we want to avoid. So we can then do a transformation here that instead of having this hierarchy here, creates another parallel state instead. And by doing this pre-transformation, the simulation becomes easier to make after that. And the simulation works by simply making random draws of the CDFs of all active states to see which happens first, and yeah, then doing that, continuing in time until we reached our specified end time. And this is, of course, repeated for many lifetimes of the vehicle or the system, as many as you have specified, which can be millions of times. Now I will take a little more time to talk about the case study. So we have, we call it the gearbox wheel lock case study. So, and it's about how would a gearbox can cause the wheels of the vehicle to lock up in driving if some internal wheels are locked when they shouldn't be. And this can happen if two internal errors occur. And that's if we have a SCB fault and an SCG fault. Short circuit ground and short circuit the battery. Now, when one of these faults appear, we have a diagnosis that can catch this. And if we notice this fault, then the vehicle will be locked in its current gear in order to make sure we don't lock the wheel in driving. And then this will be the case until the vehicle has been fixed. Now, the diagnosis in itself is not perfect. It can miss some faults, which you can see here. It's only 99% of the faults that are detected. But the diagnosis in itself can also become unavailable. And there is a diagnosis of this in term that every startup of the vehicle check if this diagnosis procedure seems to be functioning as it should. Finally, we have this component here that keeps track of whether we have reached downstate or not. So this is a short explanation. If you want more information about any of this, or the case study, for example, you can read the paper. And to conclude, Stateflow today has no explicit support for modeling stochastic properties, while it's very well used in industry. And this is why we presented SSF models which extend Stateflow with the support. We presented the SMP tool, which can perform transient and sensitivity analysis of SSF models. And as a final contribution, we applied SMP tool on a case study from the heavy vehicle manufacturer Scania. And future work includes studying the underlying stochastic process of SSF models. Thank you.